and welcome to another optimization use case for the ultra low power workshop. Today we're going to be talking about optimizing the SecureMark TLS core. Basically what is going on when you do an HTTPS connection. You have to use this algorithm, and it takes quite a lot of work to do it, and we're looking at optimization for that particular part of the code. So, Embassy is the Embedded Microprocessor Benchmarking Consortium. I'm an external advisor for the Embassy on ultra-low power benchmarks. And this particular SecureMark TLS benchmarks aims to measure the energy consumption of a typical TLS operation on an embedded platform. So, think setting up an HTTPS connection. There's a lot of cryptography involved in that. So careful tuning without even changing the code gives us 9.4 times lower energy consumption, and that's quite significant. So when we try to optimize, there is a lot of stuff that's going on. We have all these disciplines, hardware, software, radio, you name them. And in this particular case, we concentrate on compiler and compiler settings, and some hardware settings, and the rest is not involved in this optimization exercise. But even though that gives us still a lot of possible optimization. So looking at this Embassy SecureMark TLS thing, there's a number of encryption benchmark code that we need to run and measure and say, okay, what is the total sum of all of this? So we execute these partial benchmarks, compute the amount of energy, and add all that up, divide 1000 by this energy, and then we have a figure. And the higher the score, the better, meaning less energy was used to execute these tests. And all of these algorithms will be run for at least 10 seconds to minimize any measurement error. So I was asked to optimize this initial implementation using an ARM embedded system on a Nucleo processor board with an STM32L4A6Z processor, which is an M4F optimized for low power. So we use the IDE, the Atomic True Studio, CubeMX for the initialization code, and version 1.12 of the specific L4 library. Looking at the hardware architecture of the MCU, we see that there are a number of things operating at the same time. Like we have the ARM core with floating point processor, we have two DMA engines and another 2D DMA engine to operate as masters, and we have a flash, two SRAMs and SRAM3, and a lot of peripherals as slaves. So we have a 1 megabyte flash, we have 265 kilobytes of system memory, SRAM1, and we have another 64K as SRAM2, which is good for putting code in there. We don't use the available crypto hardware because we didn't have the driver code to use that, so it's all the software implementation. We can run at 80 megahertz if we need to. We have an external crystal at 16 megahertz and an external 32 kilohertz crystal, and there's also an internal high frequency oscillator, and we use a UItra for doing I/O, the serial ports, and we can use the phase lock loop, the PLL, to do frequency multiplication. So one of the things we need when we start optimizing, we need a baseline, which is basically the reference score to beat. And in this case, we have a baseline of 505 score. When we have a voltage supply of 3.0 volts, we have a core voltage of 1.2, 80 megahertz. We use an internal oscillator at 16 megahertz, and we multiply by 5 using the PLL. The UIrt and the GPIO clocks are on, but we only basically need that for one pin. The optimizer is set to -0, so that means no optimization. The linker is configured to have all the code in the flash and the read-only data also in the flash. There is no optimized version of memcopy and no optimized version of the memset function, which is used to initialize memory, mostly to 0. And the flash is running at 6 wait states, so that means that the flash is way slower than the CPU. So this is what we start out with, and this is the score to beat, and preferably with as big a factor as possible. So now what steps can we take in order to achieve improvement? For instance, we change the optimizer setting from -0 to -01, and this gives us an improvement of 2.65 times. So we already get a lot of gain just from this simple setting. So the next step is basically to turn off the serial port because we're not using it during the measurements, and also turn off the pin clocks, and we don't use the pins to see to check anything, so it doesn't make things not work. And that also gives us 8% of improvement. So next step is to optimize the memcopy function. From the earlier use case, we already saw that could be quite an impact, and here you see some impact, but not a lot, 2.5%. If we implement a special copy loop in internal flash buffer memory, like we talked about earlier, then it doesn't make any difference. So, okay. The next step is to change oscillator to a 24 megahertz medium speed internal oscillator, and then we don't use the frequency multiplier. But that means that we don't run at 80 megahertz anymore, but we run at 24 megahertz, and that saves also 4% of energy. Now we have some tables that are stored in the flash, and if you access the flash, that takes more time than when you access the SRAM memory for the same data. So we see not a lot of improvement, we see about 0.5% improvement. Now the question, of course, is how do I get read-only data, which is normally in the flash, and code that is also normally in the flash, how do I get it into SRAM? That means that we have to modify the linker definition file and say, okay, this piece of code, this piece of data needs to be allocated in this area of memory. So we need to adapt the default linker file to add some data. And we can do this without actually changing the code itself. So we define a new segment in the memory, which is SRAM2, which is in the code space. So we can put code there, and then it will run with maximum efficiency. So now that we have defined this memory area, we need to get the code that we want in there. And this is basically how you do that. You add some lines to the linker definition file that actually say, okay, if we have a segment called .ramfunc, then it has a start, and we put all the various functions in this section, and then at the end we know this is the start and the end where these things live in the flash, and then we copy them from there to RAM, and then they can run, they can be called. And by specifying certain names in the text segment or in the ramfunc segment, we can make sure that these are actually moved into that area. So, and the data for SRAM2 lives in the flash. That's what the last line basically tells you. Now, the fact that the code is there is not enough. We also need to make sure that it somehow gets copied into memory when the system starts up. So that is basically the similar thing that we did for code. We also do for the read-only data, where we place this in RAM, not in SRAM2, but in RAM, because that is where the data lives. We define these extra symbols so that we can actually get a successful link. And here's a bit of code that actually copies the code and the data, so from the flash to the RAM. So this is the part where we copy the code to this RAM, and we have a similar part for the read-only data. We now do a second step. We saw what happened. The improvement for the data wasn't very much, but now we make a change in the optimizer again. We go from -0.1 to -0.2, and that gives us another 6%. And now, because we are not running very fast, we can drop the core voltage from 1.2 volts to 1.0 volts. And that gives us 20% improvement, which is quite nice. And then we lower the voltage, the normal voltage, from 3.0 to 2.4, which gives us 26% improvement, just like that. Very nice. Then what we do is we change the memset function to an optimized version. Basically, the memset is used to zero initialize parts of memory, and that is quite an impact, changing this piece of code, 26%. And mainly the part there is used by the elliptic curve code, because it allocates and clears memory all the time. And if you optimize that, then that helps enormously. So the elliptic curve uses so-called big num functions with arbitrary length integers, and they do a lot of copying and mallocing and setting. And if you can improve that, the performance of the elliptic curve stuff goes up quite a lot, and we see a good demonstration of that over here. Next step, we move the supply voltage from 2.4 to 1.8, and we have 39% improvement, which is almost exactly the ratio between the 2.4 and the 1.8. So any change in this supply really works out very much in the actual energy consumption. So if we add all this stuff up, then we get a winning combination, and the score is from 505 it went to 4,750. So we can look a little bit more. So we should be at 1.8 volt and not 2.4 volt, but we have the core voltage at 1.0, 24 megahertz. So the end gain is 9.4 over the original implementation. We didn't touch the code. The only thing we did was move some code into SRAM in the code space, and some fairly used constants in SRAM. And we changed the optimization of some of the code so that the big num code and the elliptic curve code is optimized with -0.2, and all the rest. The big num is -0.3, and the rest is with -0.2 to get an optimal combination of optimizations, so that we get to a minimum execution time for all our benchmarks. Now, what can we conclude from this? In the various steps, we've improved the initial score by 900%. The biggest gain was just by reducing the voltage, where you can see that the energy scales linearly with the voltage. There's also a big gain by turning on the compiler optimization settings, and we have very small gains by moving code and data into the SRAM. Also unexpectedly big gain by selecting optimized library routines, and then we have a lot of small gains, and all in all you get a very big total gain. So when optimizing for power, try and use as low a VCC and core voltage as possible, and then maximize the frequency within those boundaries. And maybe if you're running with wait states, you can try and forget about them for the lower frequencies, because then they are not necessary anymore. So the best thing might be to say, okay, how fast can I go within the voltage conditions without any wait states? And that's also, again, measure the performance and see what you get. Now, flash is more expensive in terms of energy than SRAM, but unfortunately there isn't always enough RAM to completely run all the code from there. So the critical functions you would like to have run in SRAM, preferably mapped in the code address space. So in this particular example it's SRAM2, and the critical read-only data to the SRAM, which is in the data address space, system address space. Turn off all the clocks to peripherals you don't need. Watch out that there are no floating inputs because they can draw milliamps apiece. Check all your optimization settings for the code that you want to try and optimize, and select specific optimization for the critical files, so you can optimize by file. And try and use optimized mem copy, mem set functions, because many other functions use them, and if you improve there, you could also improve a lot of other things just in one go, and you don't have to touch any of the code to be able to do this. And that's it for this use case. Thanks very much for your attention.